Okay, hi everyone. Let's get started. So last time we were discussing pseudo-random generators, and if you remember, we were able to construct a pseudo-random generator with just a single bit stretch, right? So the pseudo-random generator was able to take like a n-bit seed or n-bit input and was able to stretch it to just n plus 1, right? So we want to do better, and it's not very difficult to do better by just applying this process iteratively. So today we will start with the goal of constructing polynomial stretch pseudo-random generators. So our goal will be poly stretch Prg, right? So we need to construct a function, let's call it GP, which takes an n-bit input and stretches it to L of n, where L of n is any polynomial in n. It could be n square, n cube, or whatever you want it to be. And we will assume that we are given a PRG from the last class, which is just one bit stretch PRG. Okay, so how does GP work? GP takes as input seed, okay, and it works as follows. So as you can expect, we will apply G once and we will get n plus 1 bits. Then we will take n of these, apply G again, that will give us further n plus 1. So in every step, we are sort of getting 1 bit for free, and we will keep accumulating those bits. And finally, we will have an output which can be as long as we want.
So the polynomial stretch PRG, right? So this works as follows, essentially what you would expect. So we'll do it in many steps. So if we need an ln bit output, we will basically have ln steps. So in each step, we will select a new seed. So the first seed, which we call S0, is basically the same, which is given to us as input. And then what you do is you apply G of S, and that gives you an n plus 1 bit output. And that will give us our next seed, which is S1, and it will give you an extra bit. Let's call it a free bit, which will appear in the output. Okay, so we keep B1, and then you apply G to S1. This was S0. Then you get S2 and B2. And finally, you have GS of ln minus 1. And that would give us S of ln concatenation B of ln. Okay, so now we have accumulated enough free bits, and we will just output these. So output B1 concatenation B2, finally BL of n. Okay, and these are L of n bits, which is exactly what we wanted. So a couple of observations to keep in mind. There's a question in chat. Okay, good. Yeah, I was just getting to that. The question is, so in various intermediate steps as well as the last step, we get various seeds. So an observation is that it is not safe to use intermediate seeds. So for example, let's say I give you an intermediate seed, let's say S1 or let's say S2. So given S2, one can actually compute B3, S3, B3 and all subsequent bits as well as subsequent seeds. So you don't want to have S2 in the output. But on the other hand, you can include S of ln in the output if you wanted to, right? So that would increase the output by further n bits. Doesn't really make a difference. So just for cleanliness, we don't include it in the output. We just include these free bits, and that's what our output would be. And now let's try to analyze this. Okay. Now my claim is that GP is indeed a PRG.
Sir,
Yeah.
could you please re-explain this note? I could not properly understand it. Like, why is it not safe and what does that mean? Could you please explain?
Okay. So we are generating these intermediate seeds, right? So let's say I include the first seed, let's say S1 or S2. Let's say I include S2 in the output. Okay. But I still continue including all these subsequent bits. But given S2, these bits are not random anymore, right? Because given S2, I can compute S3, B3, I can compute S4, B4, and essentially everything after that.
Okay, I see. Thank you.
So
Thank you very much.
These bits B2 to B of ln, or rather B3 to B of ln, they are not random. They don't look random given S2.
Okay. Thank you, sir.
On the other hand, the last seed is not being used any further. So if you wanted to, you could include it in the output.
Okay, so just the last seed we can use in our output.
Yeah. So our claim will be GP is a PRG, assuming G is, right? And how do we prove this claim? Again, how do you start any proof? You start thinking about a hybrid argument. That's a strategy not just for this lecture, but essentially for the entire course. So we will define a series of hybrids. H0 is basically the same as our construction, which is GP. Okay. And now let's move on to H1. So our strategy would be, we have several invocations of G, and one by one, we will replace the output of each G by a uniform string. So HG, we will again start by the first seed being just the input. But now here comes the difference. So here, instead of invoking G of S0, I use uniform distribution to sample S1 and B1. But after that, I start using G again. And from this point onwards, I continue to use G. And then finally, you have HI, right? So up to SI and BI, I sample uniformly, and after that point, I start using my G. So now here's an interesting observation. You look at these previous strings, right? Sorry, this should be bi plus 1. You look at all the previous seeds, just the SI strings. They are not being used at all. In this experiment HI, right? Because, for example, we never used S of I minus 1. So just something to keep in mind. There's no need to generate them. And then finally, we will have our H of Ln, where, you know, all steps use U of n plus n as opposed to Prg. So there's no invocation of a Prg here. Okay?
So the previous ones are still used to generate like B1, B2, B3, right? So they will appear in the output effectively.
So B1, B2, B3, they are all random, right? They have no correlation with the seeds, and seeds are not being used to generate these bits. So yeah, you are right that we do need to continue generating B1, B2, and B3, but there is no reason to generate, for example, S1, S2, and S3.
Oh, so every single seed before I is drawn from uniform.
Sorry?
So every single seed before I is drawn from the uniform distribution, not just SI.
Yeah, exactly.
Okay, sounds good.
Yeah. And now let's, we'll have our claim that HI is computationally indistinguishable from HI plus 1 for all I. Right? And now observe that what is the difference between HI and HI plus 1? The only difference between HI and HI plus 1 is in how SI plus 1 concatenation BI plus 1 is generated, right? In HI, we use G of SI, where SI is uniform, and in HI plus 1, we have U of n plus 1. Okay? And now we can see that this basically directly follows from the security of G, that these two distributions should be indistinguishable. Okay? So given PPT A, HI plus 1, which distinguishes HI and HI plus 1, we can build another PPT adversary B, which takes as input, which takes, let's say, Y, let's call it YI plus 1. And this is from 0, 1 to the power n plus 1. Which is either output of G or is sampled from a uniform distribution. And B will set Si plus 1 concatenation Bi plus 1 to be Yi plus 1. Right? Everything else is as before. All the previous seeds, they are uniform. All the subsequent seeds, they are generated by applying a PRG. Okay? So now B will set this. And then sample all other Si and Bis as in Hi, invoke A. If A says, or rather, let me know. If A distinguishes, then B also distinguishes with the same distinguishing advantage, right? If A can distinguish Hi and Hi plus 1, then B can distinguish the PRG output from a uniform output. And that essentially completes our proof. Okay, any questions?
So I have a small question, like why are we sampling all the other SIs and BIs? Shouldn't we, like after we set the SI plus 1 concatenation BI plus 1, shouldn't we then apply the G again and again finally to give the output to the adversary?
Yeah, you don't need to sample any of the previous seeds.
No, but like for the seeds that are afterwards, like will we sample them or will we apply the G again and again? Like, so like.
Yeah, you will apply G again and again.
Yeah.
So by sampling, I don't mean randomly sampling, or maybe sampling is not the right term. I should say sample or compute.
Okay, thank you. Thank you very much.
The earlier ones are sampled, the later ones are computed.
Professor, why do we need to compute all other SIs? By constructing B, we are trying to break the original PRG, right?
Yeah.
That
So
requires
B,
just the one sample.
so B will only have one sample, but B needs to invoke A, right?
Oh, okay.
And A needs the entire PRG output.
Okay.
Which is B1 to BLN, right? So
Right.
you do need to generate all the Bs.
Okay. Thank you.
So here, as you can see, the main idea was we make such a small change that the only change was changing the PRG output to uniform. And then you can just rely on the security of that particular PRG invocation, even though we use the PRG many times. So this is why hybrid argument makes things very convenient. So now we have done something which is very nice. Now we have a PRG which can take a small uniform string and can convert it into a very large string, which still looks uniform to a PPT adversary, right? So now let me come back to one-time pad. So what does this allow us to construct? So a major limitation of one-time pad was that your key had to be as long as the message, right? So imagine your key is like 100 bits, your message is 1 gigabyte. One-time pad just completely fails. But now the nice thing is applying a PRG first on your key allows you to stretch your key to whatever amount you like, and then you can use one-time pad to encrypt a message which can be as long as you want, right? So a very rough construction. We will come to encryption schemes more formally, and we will discuss it in more detail at that time. But just just to give you an idea of one application of PRG, is that it allows us to build one-time pad for, let's call it, long messages. Okay. Now let's assume that your key is K. I'm just writing things informally, and let's say your M is larger than K. It can be much larger than K. Okay. Then what does your encryption do? Encryption will take K and the message, and the encryption will output M XOR GP of K. Okay, so you apply a PRG such that the output length is equal to the length of the message, and then you are ready to encrypt the message using one-time pad.
So if I'm sending this message to you, then how will you make sure that the generating, like I generated a key of length M on my side and you also generate something of length M on your side? How will we make sure that both of those things are same?
So you will need to agree on size of the message.
No, but even if we agree on the size of message, since it's probabilistically, it's a probabilistic randomly generating the key, right? It might generate one key for you and one key for me.
So look, in encryption schemes, you and I have to start with the same key, right? You are the decryptor, I am the encryptor. We share key, right? So Alice and Bob share the key K. And let me finish the decryption. I think maybe it will answer your question. So the decryption procedure will take K and the ciphertext, and then it will output C XOR again GP of K. If both of us have K, both of us can compute GP of K, and remember the PRG is deterministic, it's not randomized.
Okay, I understood. Thank you.
And of course, this kind of encryption scheme is not going to satisfy perfect security, right? Perfect security refers to unbounded adversaries, which can obviously completely break the PRG. So what kind of security would this satisfy? Intuitively it does satisfy something good, but we will see when we come to encryption schemes, how we can define encryption schemes for PPT adversaries. And there are various notions which we'll look at. But there's still a limitation here. So what is the limitation? It is still one time, right? The problem is, of course, I can make my key as large as I want, but once I use my key, it's used up. It cannot be used again.
Couldn't we just keep generating further bits of randomness? And
Exactly.
that if we wanted to encrypt 5, oh, okay.
Exactly. So that's a good point. So you can do that. Yeah. Yeah, you can divide your PRG output into many parts, use the first part, then use the second part, and so on. So one problem with that is that encryptor and decryptor, they need to be in sync all the time. Like if the order of the messages gets reversed or something happens, the scheme fails. So that's one problem.
Mm-hmm.
And in fact, we can even assume that there might be a single encryptor and multiple decryptors, right? So I am the commander, I'm sitting at home, I'm giving commands to many different soldiers who might be at different locations. So in that case, it's not clear how they can all maintain the same counter. They don't talk to each other, right? But on the other hand, you can even include the counter publicly in the ciphertexts. So yeah, we will see how that is done. But ideally, there might even be multiple encryptors, multiple decryptors. So things kind of maybe you can make them work, but not an ideal solution. So a much better solution is using pseudo-random functions, which we will study next. Pseudo-random functions are a generalization of PRGs, and in some sense more powerful than PRGs, and yet they can be constructed from PRGs. Okay. So another thing I wanted to mention is that there's a very nice result by Impagliazzo and Luby. So in our construction, we used one-way permutations, right? We used one-way permutations to build one-bit stretch PRG, then we generalized it to poly-stretch PRG. But maybe we can imagine a world where one-way permutations, they don't exist, but maybe one-way functions exist, right? For example, from factoring, we were able to construct one-way functions, but we haven't even seen one-way permutations so far. We will see that later. So Impagliazzo and Luby proved a very nice result. So they built PRGs from just any one-way function. And one-way function is really like the most basic primitive in cryptography. And it's nice that this basic primitive is sufficient to construct something which is seemingly more powerful, something like PRG. Okay, so now let's start talking about PRFs. Pseudo-random, not generators. Now we'll talk about pseudo-random functions. So here the idea is that we want to use a single seed or a single key to generate a very large number of random strings. Okay. So, you know, one option again is generate a single random string, chop it into many parts and so on. But pseudo-random generators can actually even let you generate an exponentially large number of random strings. And why do we care about that? So pseudo-random functions, in some sense, they are a cryptographic equivalent of random functions. Graphic equivalent of random functions. And what is a random function? A random function, let's call it RF. It takes some input, let's say M1, and it gives you an output M2. A random function is deterministic in the sense that if you query it with an input multiple times, you will continue getting the same answer. So a random function can be visualized as a table. Okay. How many entries does the table have? So a table looks something like the following. Table has many entries and all 0. One, and so on. Okay, so this will be 2 to the power M1 entries. And these are all random strings. Okay, so it's a table which maps each input to a uniform output. Okay, there's no further logic to that. Just take every input, generate a random string, and that is what the output will be for that input. A random function stores this entire table. You give it some value x, it looks up the value of x on the left, and it outputs the corresponding string on the right. Okay, is the definition clear for random functions? And even though, you know, Random functions might look simple. They are huge objects. You cannot store random functions. Hard to store. Right? So think of M1 as like, let's say 100 bits. Then you're talking about storing 2 to the power 100 entries. So which is just an exponential amount of storage is something which is needed. Is it similar to random oracles? Yes, exactly. It is random oracle. Is it one-to-one? Not necessarily. There's no properties, just basically every output is uniform. But the thing is that if you give the same input twice, you will continue getting the same output. What is the difference between PRG and PRF? We will see the definition of PRF. Okay. So a random function is hard to store. These are exponential sized objects, right? But it would be nice if we could construct a function which we can actually store, and the function would behave like a random function. And that would exactly be what PRFs would allow you to do. Okay. So a PRF is a function which actually takes a key. The key will be 0, 1. The key will be n bits. And it will take another input, M1, and it will give you some output, M2. Okay. So key is supposed to be secret. It will stay, whoever generates the CRS, it will stay secret with them. And then anybody can query this function f. And anybody who queries either a random function or this function, pseudo-random function, they cannot tell the difference between these two. Okay. Yeah, so the difference between PRG and PRF is that a PRF takes 2 inputs. So it can also be seen as like a random access PRG. So imagine a PRG which gives you an exponentially long string, and you are able to access any position of that. And the second input tells you which position I'm interested in, and it will give you the string in that position or bit in that position. Okay, so now maybe let's try to define PRFs a little more formally. So let's see here, the PRF definition. Okay, so a function f So typically we will denote this by the key or seed. You can also call it S, and the position or the input is X. So this is called a PRF if the following conditions are satisfied. So first, as usual, F on every input runs in polynomial time. and it is deterministic. The second condition, what do we want? So here the second condition is a little bit interesting. So we want the output to look something like uniform. So maybe I need for all x f of, okay. So let me try to give you a definition which will not work, but hopefully you will tell me why it will not work. Okay. So consider the following. Distribution f of k comma x, where k is sampled at uniform, and this is for every x. This looks computationally u of m2 for every x. So essentially what I am saying is, if the key is indeed generated at random properly, then for every x you list all possible outputs, and that should look indistinguishable from the uniform distribution for every x. Is this a good definition? Any problems?
Essentially, for a given key, the function could be very non-random and like always return the same output, just well distributed over the space of keys.
Well, you could have said the same thing about PRGs, right? So that's always the case. For encryption, for example, let's say
Yeah.
I choose some bad key, encryption can be bad. So we only require security to hold for uniformly generated keys. So what else? So look at the size of this sample. I'm basically taking the function output in every possible x. I'm concatenating all of that. And I require that this huge string should essentially look uniform. Right? The problem is this is exponential sized, right? So imagine a hybrid argument where we will take x one by one and we will replace the output by uniform. So we will end up going through an exponential number of hybrids in that case. And in that case, it's hard to talk about computational indistinguishability. Even if two subsequent hybrids, they are close to each other, negligible advantage and so on, the overall sum could be huge, right? And in fact, as long as we are talking about PPT adversaries, they cannot even take, for example, this distribution as input, because even reading the input requires exponential time. So this is not good. Let's get rid of it. We need something more clever. So even though there are exponential number of possibilities for x, right? A PPT adversary can only make so many queries, can only choose so many different values of x, can read the output, right? So we will just focus on those queries. Okay, we will require for every PPT A, probability that A wins in the guessing game, which I'll just define, should be less than or equal to half plus negligible. Okay. And just looking ahead, what is the guessing game? In the guessing game, the adversary interacts either with a random function, making polynomial number of queries, or it interacts with a pseudo-random function. And this adversary cannot tell the difference between the two. So the guessing game is defined as follows. Guessing game is as follows. Step 1, there is an adversary and then there's a challenger. Okay. And we will see how that makes sense. There is a random key K and a random bit B. So the challenger A queries. Step 3 is A queries with some xi in 0, 1 to the power m1. Now, depending upon what B is, if B equals 0, challenger responds with the Prf output. So f of k comma xi. If B equals 1, the challenger uses a random function. Okay. So let me explain the point number 4 once again. So the challenger chooses a bit B, and depending upon that, the challenger decides either to use this the pseudo-random function or use a random function, right? A random function doesn't necessarily mean that you don't even look at the query, you generate something random and you give it out, because the answers have to be consistent. So you see if xi has been queried before, which means that xi equals xj for some j less than I. And if so, you give the same response. Else, sample from u of m2 and respond. Okay. And by the way, this step 3 and 4, these steps can be repeated any polynomial number of times. And then finally, A outputs a guess B prime and wins if B prime equals B, right? So throughout the experiment, A can make several queries. All of these queries are either going to the PRF or going to a random function. And then at the end, A has to guess what it was interacting with, right? And of course, A can always win with probability half without making even any queries. So what we need is the probability of A winning to be less than or equal to half plus negligible. And then looking ahead, the way we can hope to prove something like that is by just doing a hybrid argument over the number of queries. So we will try to replace the response for each query from PRF to uniform. And finally, we will start with the PRF. Finally, we will end up with a purely random function at the end. And because there is only polynomial number of queries, our number of hybrids will be limited to a polynomial again. Okay, so now let's try to build a PRF. And we will be able to build a PRF from any PRG. So what we will use is so we are given a PRG, let's call it G. Which doubles its input. So it takes an n-bit seed and converts it into a 2 n-bit output. And we will build a function which will take an n-bit input and it will take an m-bit index and will give you an n-bit output. But you can generalize to basically any output length later on. So let's warm up slowly. So say m equals 1. Okay? It's just a very simple case. How do we do it? So denote G0 of k to be first n bits of G of k and G1 of k to be last n bits. So any ideas on how we can handle the case when m equals 1?
Return either 0 or 1.
Yeah.
Well, G0 or G1.
Yeah.
Exactly. Yeah. So in this case, f of k comma x is just gx of k. Okay, x is 1 bit. Yeah. Now let's try to go to 2 bits. What can we do here? Any ideas? Well, maybe we try to use recursion. So this is G00 k if x equals 0, 0. Sorry. Okay, let me just write it as G of x2, g of x1, k. So here xi is the ith bit of x. So you look at the first bit. Depending upon that, you select either G0 or G1. Your output is uniform, so you can apply this process once again, and again select either G0 or G1. So I can write it in the form of a tree. So this is your K, and this is G0 of K and G1 of K. And now again, these are n-bit seeds. So this is G0, G0K. This is G1 of G0K. And then similarly here. This will be G0, G1 of K. And the last will be G1, G1K. Okay. So you look at your input. You basically choose a path in the tree. Each input represents a path in the tree. Okay. So let me describe to you the final construction for any input length x. Okay, I think the definition of guessing game is simple enough. So here is our final construction. F of k comma x looks like the following. So the last the last invocation is just g of xm km, and that gives you k minus 1, and this is your output. Okay, and we can extend our tree further. So many leaves, and depending upon what your input is, you start with the root. You either go left or right, depending upon whether the next bit is 0 or 1, and finally you end up with some leaf of the tree, and that gives you the output. Okay, so hopefully the construction is clear. Any questions about the construction? Now, how do we prove that this whole thing is secure, right? So this is a slightly not so straightforward hybrid argument, but still not so bad. So there are two things to keep in mind. So first of all, we cannot hope to take this whole tree because it's exponential size. We cannot hope to replace each leaf by uniform. That's not what we want to do. We only want to look at the relevant leaves which were queried by the adversary, and we want to just replace the content on those leaves to be uniform. That would be our eventual goal. But there's another problem, which is that each leaf actually involves a whole path, right? Each leaf is not generated using a single invocation of the pseudo-random function g. Each leaf essentially involves basically m invocations of the pseudo-random function, right? So we don't want to replace all of them by uniform in one go, right? We want to take one g at a time, and we want to replace it by uniform. Okay, So our strategy at a high level would be, we will start from the top for each query, and then we will replace at the first level, we will replace PRG output by uniform. Then we will go to the second level, replace PRG output by uniform, and we will continue the strategy all the way down. Okay, and we need to do this for every query. So we will actually go level by level. So in our proof, we will consider the following set of hybrid arguments. So H0 is our original tree. In H1, we look at all the nodes which are relevant or which are queried at level 1. So all queried nodes, let me say up to level 1. Are uniform, and then apply G for all subsequent levels. Okay, and what is HI? So I'm calling this level 0. This is level 1, 2, and finally we'll have level M. What is HI? All queried nodes up to level I are uniform, and you apply G for the subsequent levels. Makes sense? Now, something to observe, you look at level I plus 1 and above. Nodes at level, sorry, I minus 1 and above, don't play a role, right? Because what is the role of nodes at level I minus 1? You apply PRG and then you get the nodes at level I. But nodes at level I are already uniform here, right? So essentially you are like cutting off some upper part of the tree. You don't even need to sample uniform strings for that. I can just directly sample uniform strings for level I. I don't need to care about the top half of the tree. And then finally, we will have our level HM, where all nodes at level M are uniform. And again, we are only talking about queried nodes. So now what does HM correspond to? In HM, every query selects a leaf or a node at level M, and each node is basically uniform. So in HM, here, all queries answered as per a truly random function now. So we are starting with a PRF, and we basically changed the answer of all the queries to a random function. The output length of F is N or M. It seems if M equals 1. Yeah, the output length is always N. And this comes from the fact that the output length of G is 2N. Okay, so you will apply G, you will basically like get two children, each having output length N. Output length doesn't depend on X or its size. Okay, any questions? So now let's try to look at the proof of this construction. Let me see if I can continue using this board. So let me just keep the tree and erase the construction. Now, note that if you look at hybrid I and hybrid I plus 1, right? We are in a single step, we are still replacing several PRGs by random because there are many queries. So that is still not the best which we can do. So even between hybrid I and hybrid I plus 1, we will define even more hybrids. Okay, so now our claim is, let me write it here. Hybrid I is computationally indistinguishable from hybrid I plus 1. Now, what is the difference between hybrid I and hybrid I plus 1? The only difference is in the I plus 1th level. Okay, so in I plus 1th level, in hybrid I, they are PRG outputs. In hybrid I plus 1, these nodes are uniform. So HI0 is the same as HI. HIJ is, let me write HI1 actually. HI1 is we look at the first query. That first query will select some node at level I, or rather I plus 1 for first query. The node at level I plus 1 and its sibling. Is selected uniformly. Now maybe let's look at the tree, and let's say this was level I and this was level I plus 1. Okay, and let's say your query goes something like this. And then it follows some path in the tree. Now what I'm doing is I am removing this invocation of the PRG. This invocation of the PRG resulted in these two nodes. They are siblings of each other. So now I remove this, and instead I select this node and this node uniformly. So these are nodes at level I plus 1. This is the selected node at level I plus 1. This is its sibling, and we choose both of them uniformly. And now the nice thing is, if you look at HI0 and HI1, I'm only replacing one invocation of the PRG with a uniform output. And now I can use PRG security. And then you keep going like that. And then finally, we will have HI of Q, where Q is the number of queries. And then for the last, or the Qth query, node at level I plus 1 and its sibling selected uniformly, if not already changed. So it is possible that two different queries will end up selecting the same node. So in that case, it's possible that it was already changed to uniform. If that is the case, we do nothing in this hybrid. So now this hybrid is the same as hi plus 1. Right? And if we can show that each subsequent hybrid is computationally indistinguishable, then basically hi and hi plus 1 are also computationally indistinguishable. And if you compare any two subsequent hybrids here, you can immediately use the security of PRG now. Because, for example, in hybrid hi0 and hybrid hi1, the only difference is how these two values are selected. Earlier, they were output of the PRG, and now it's just two uniform strings. So given an adversary A, which can distinguish these two hybrids, you can construct another adversary B, which takes a 2n length string and puts them here, right? If they are PRG output, we are in this hybrid, otherwise we are in this hybrid. So if you can distinguish these two hybrids, I can distinguish uniform from the PRG output. And that's essentially the whole argument now. Any questions? So essentially what we have done is we have taken sort of PRG, which sort of stretched the randomness by adding polynomial factor, and PRF, in some sense, stretched the randomness by an exponential factor, even though you don't access all of it. But if you look at the whole, like all the leaves put together, there's an exponential number of random strings. And this would really help us actually in building encryption schemes. We will see that later. So just to give you a sneak peek of how this can be applied to encryption. Now what you can do is, let's say I want to encrypt various different messages, right? Every time I can just use a random index. I don't have to remember any of the previous indices. And just because there's an exponential number of indices, the probability that I will use the same index twice is now negligible. Okay, so encryption, what does it look like? M and K. So select X at random. And now your ciphertext is, it contains X in clear, and it contains the message and the PRF output K, X. Okay, how do you decrypt? Look up X from C, recover F of K, X, and recover M. So this is like a one-time pad key, and we are almost guaranteed that we will never use this one-time pad key twice, because you are selecting X at random and X is large. And again, we will look at this this encryption scheme in more detail at a later point.
But this scheme does not work for long messages, does it?
Well, depends on what the length of the PRF is. Yeah, you are right. But if the message is long, I can additionally also apply PRG here.
Okay. I mean, so
let me write a general note, actually, just generalizing PRFs. So how do I construct a PRF with a much longer output length? So it takes N, it takes M1, and the output is M2, where M2 can be much larger than N. So far, I constructed a PRF where M2 and N are the same, right? So there are multiple options. So option 1, start with a pseudo-random function, which takes an n-bit input, but now gives you 2 M2-bit output, right? And now the length of each leaf will be M2. Or another option is apply GP to the PRF output, and then you can stretch the output to any desired length, whatever you want. Okay, so we will stop here. I'm still around for questions.